I follow from top in a way and talk about we add moisture and clouds to this talk. Also, this is my motivation and convective organization. I hope people knows how to look at this image, geostationary satellite infrared image over Western Pacific. So we see a bunch of clouds organized into planetary scale. Here is Australia and China here, somewhere around here. And so question is, how this convective organization shows up? Sorry. I think this is a good talk for this workshop because we see very interesting topic of eddies and waves. But of course, main question is how convective organized into this form and how maintained. And we take energy cycle analysis in waves. Start the outline. So this explanation we take the down one. Please follow it. And Steve will know. And it starts from random state, third persuasion with homogeneous SST with no rotation. Just with the day one precipitation field, we rather see convection develops as seen as a precipitation field in day two. We see these convective variability cluster around gradually. In a few days, and day 8, we see a very well organized convective cluster. But somehow it breaks down just 1 day later, and it takes another 10 days to recommence again, and takes this wave for another 30 days. This is day 30. And questioning how this happens. So the analysis field, we go into the wavelet space analysis. And reason is it's spatially coherent, localized in space. So we should use wavelet that are designed to decompose spatially isolated structure. But important point is essentially same thing as Fourier. It's discrete, also gonal, and we can use almost same principle as Fourier, but with localization in space and different scales. So it's consisting of 2 indices. First indices is in direction of space scale, wave number increased by twice. This first one is wave number 1, you get wave number 2 and 4 and 8 and so on. And corresponding to given wave number, you get with wave number 2, you get 2 localized. Wave number 4, you get 4 localization. And with 8, and so on and so on. And imagine, important point, this is complete set. So imagine you get 16 data point measurement in time. Then you get, I hope you can count 8 plus 4 plus 2 plus 1, make 15, plus another node, average, time average. You get 16 more, describe this full data set complete. In this sense, this is complete, and because also now, like wavelet, it's easy to do the decompose. So in that extent, it's same as Fourier, except for we can do analysis for isolated structure. Like this example, this is time series over Western Pacific, just for example, about 3 years, with zonal wind of a tropic, of course, and we see a very strong burst of zonal wind, westerly, so-called westerly burst. And this is a time series with this wavelet coefficient in wave number and localization. And you see some clustering corresponding to those westerly bursts. Focus on particular scale, 40 days, you see some clustering around here and here and here. And you can extract those clustering by certain methods, by identify a local maximum of wavelet coefficient, and then gather those significant mode round, and you can extra 4 pulse mode. Because this is complete, we can invert back to your space, and you see a 4 wave burst event well exacted by this wavelet method. And we use this method in space. In spatial section, we do wavelet decomposition in 2 directions, X and Y. That's the principle. And first thing we look at is simply evolution of spectrum in wavelet space. So we sum up all the localized mode in X and Y, and this evolution of precipitation field with time. Then we see a precipitation power gradually evolve with time. But funny thing is, we never see this energy goes to smaller wave. I'm sorry, I forgot. This wave number in X and Y, and wave number increased by factor 2, as I said. So power increased with time, and I stopped at day 7 because this structure never changes from this time. Although we do see convection organized into large scale in I, but this is wisdom to learn. What you see with I is not always showing wave number space, and that's the example. But interesting is if you look at kinetic energy spectrum, this essentially U squares wavelet coefficient, then energy goes up to upscale, taking just a couple of days and stay this way. So we see the evolution of kinetic energy organized into larger scale with time. So the question is how this happens. So here I switch question of duration convective organization into how kinetic energy P shift to the larger scale with time, and try to answer this question. To answer this question, how this happens, we look at energy cycle. So energy is generated by direct heating to generate potential energy or variable potential energy exactly, and buoyancy duration effect convert potential energy to kinetic energy, and kinetic energy to stay out. So we got sign S for double meaning. It stands for source and sink. So, and conversion is C and so on. And this is for single scale. We can consider very large scale and small scale, and ask the same question that potential energy is generated by direct heating in various scales, and then converted into kinetic energy at other scale and dumped out. But there are nonlinear induction from small to large, both with kinetic energy and potential energy as a nonlinear terms. And we are going to do this with the conversion into scales and also localization in wavelet space. And key question we ask is how this shift of energy from scale, small scale to large scale. Is it? So there are 2 possibilities. Because convective forcing for this system moves from small scale to large scale with time, well, or alternatively, there's something nonlinear equal. So that's the question to ask. Now, this is some notation. Kinetic energy defined in standard way is subscript L with index for wavelet mode, and here is wavelet coefficient. And one thing is available potential is defined by in terms of future potential temperature. That's made of buoyancy, and sigma is made of stratification. And important thing is this energy cycle, kinetic energy is generated by potential energy by buoyancy forcing. So buoyancy multiplied by velocity generate the kinetic energy from potential energy. That's the key process to remember, and direct heating generates potential energy. And in this definition, we define nonlinearity as a tendency. So that's something we have to remember. It's hard to do the transfer formulation, so that's we compromise. So I'll discuss forward. And this kinetic energy budget for average for the first 10 days. First is conversion from potential energy by buoyancy duration term, and this dissipation term. Negative is dissipation. then first thing you notice, converging energy, kinetic energy is immediately split at the same scale, almost same amount, but this is slightly smaller. And fourth thing is always dominated at small high wave number, and most imbalance is fading out, but tiny imbalance gives a nonlinear transfer. And what we see is at small scale, energy lost by nonlinear term and transferred into larger scale. So short answer for this shift of peak to larger scale is not due to the forcing of buoyancy at larger scale, but rather by nonlinear energy or transfer from small scale to larger scale. In short, by inverse cascade. Just look at potential energy budget. This is fairly complicated and very unstable in data stage. And generation is not intuitive. There's huge sink at large scale and converging as we see. And nonlinear transfer is fairly complicated. What the conversion from horizontal and vertical looks like forward cascade. Anyway, so main point is large scale ionization is controlled by inverse cascade of kinetic energy from small scale to large scale. The next question, how this happens? So we get back to this wavelet and try to figure out what's going on. So we decompose all bunch of variables into wavelet space, and we do kind of process decomposition. We pick up certain threshold variable and decompose whole variable depending on this threshold variable is large or small. So to say, high component and low component. And as a specific choice, this threshold variable, we take conversion rate of potential energy to kinetic energy. So high component is, so to say, buoyancy-driven component, and low component, non-buoyant-driven component, and repeat energy amount. And first thing to notice is kinetic energy of buoyant component is very large in respect to non-buoyant component confined to small scale. But this is already puzzling because conversion potential energy, kinetic energy, is going at small scale. But what happens is, although buoyancy is kinetic energy from potential energy, that is immediately converted kinetic energy, and somehow this is non-linearly transferred from non-buoyant component by transport of this non-buoyant component into buoyant component at large scale. So this is very twisty story. So this kind of summary, what I just said. The kinetic energy generated from potential energy by buoyancy term into convective buoyant component, but we see only small contribution to this forcing scale, but this immediately converted into non-buoyant component. That is somehow nonlinearly transferred into buoyant component to large scale. And we look at this nonlinear tendency, and I don't show it because it's messy to show. We can show that this nonlinear transfer is mostly coming from nonlinear induction of those non-buoyant components itself. Self-induction of non-buoyant component drives this nonlinear inverse cascade. Now, so question is, what is non-buoyant component? I think if you're intelligent enough, you can imagine what we will see. So just the what's going on in real space. It's all wavelet space analysis, but we now have to consider non-buoyant to buoyant component, and we see how those two fields look like in real space to see how it's going on. So upper plane is buoyant component of vertical velocity, I think 5 kilometers level, and buoyancy field of future potential temperature, and same for non-buoyant component vertical velocity and CW. So we see a bunch of convective power localized with associated positive buoyancy. That is reasonable, but we see this ring-like structure propagating upward with time. And if you think carefully, this non-buoyant component means there's no conversion from potential to kinetic to the buoyancy. So it's kind of energy conserved mode. So it's free mode. And free mode in this system without rotation is only possible as gravity waves. And we see this gravity wave leading away from convective powers. And those nonlinear gravity waves drive the inverse cascade into large scale to generate convective ionization. So that's appear to be first column. So this is for skeptic audience to show phasation vertical velocity and CW field for the case I showed for particular section. And this another stuff from another structure that show vertical velocity and buoyancy field are roughly in off phase to kind of prove this actual gravity wave. So this is what I like to summarize. So we see a bunch of convective power generated, and that generates gravity wave, and this nonlinear gravity wave dynamics drives the nonlinear energy transfer to large scale. That is to convective variation. And that's the way convective harmonized in this system, as we have seen. I hope it was clear enough. Vielen Dank.